Before we begin talking about section 4.2, I wanted to remind you that all of chapter 4 is about a new thing, a very important thing in linear algebra called vector spaces. I mentioned there were 10 axioms at the beginning of chapter 4 that I didn't point out, but I wanted to show you what they look like in your book and just mention a few things about this. First of all, this is the definition of a vector space. If these 10 axioms or these 10 rules are met, then you have your vector space. I want to remind you also that for the most part, when you hear the word vector space, I want you to think of something that's most familiar to us, like R3 or R2, though it can be something else. But to give you something to hold on in your head, imagine all of R3. That's a vector space. Here's some other things. A vector space can't be empty. It has to have something in it. And these things, objects, are called vectors. Now notice I like how this definition puts the word vector in italics. It's not exactly what we usually think of as a vector. I mentioned last time a vector could be a matrix, or it could be a polynomial of degree 3 or less. So just be loose in what you think of as a vector. Whatever these objects are, they get to be called vectors. The two big operations that happen, vectors can be added and then they can be scaled by real numbers. So real quick, just looking at this list of 10 axioms, I don't want you to see this as just 10 random rules that must be followed. There's a nice structure to this. If I were to draw a line halfway through the list, you'll notice that the top 5 all have something to do with addition. In fact, the very first axiom is the closure axiom under addition, meaning if you take any two vectors and if you add them together, the result is in that set. So that's the biggest idea of those first 5. The other 4 are important. They seem somewhat intuitive. They look like they came from an algebra class. We've got commutativity, associativity. It must have a 0 vector such that. Then look at the bottom 5. These 5 have to do with multiplication. So if I were to identify the key axiom, if you scale a vector, its result must be in that vector space. So, just wanted you to see this is what those 10 axioms were. 5 are related to addition, the other 5 are related to multiplication. And then to remind you that we're going to explore more than anything are subspaces. And if you can remember the 3 most important ideas, what makes a subspace is you first have to start with a set of vectors. And if that set includes the 0 vector and is closed under addition and closed under scalar multiplication, you've got your subspace. So, moving on, 4.2. We're going to do this in parts. We're going to learn about a very important subspace related to matrices called null spaces. So first, to get you aligned with something very familiar to us, here is a system of equations with 3 unknowns. We call this a homogeneous system because each equation equals 0. And it won't be a shock to you to see we can turn this system of equations into a matrix equation. I want you to predict what this is going to look like before we reveal this. So we've got this system of 2 equations. What's the matrix lurking in here? What does x look like? And what does the 0 vector look like? Well, the matrix itself is pretty much laid out the way we see it up here. We've got 1, -2, -1, -3, 6, and 5. Just the way those coefficients look. So what is my x vector? Well, it's the components of my three variables that we don't know. So x1, x2, x3, and finally the result is the 0 vector, which is 0, 0. So, what is it we're looking for? What is this asking us to do? This is looking for a vector in R3 that gets sent to the 0 vector in R2. And we know there's at least one solution to this, the trivial solution. But what we're more interested in is if there's more than just that. And so we now have the set of all these. Think of all the solutions that would make this true. That is what's called the null space of matrix A. Is the set of all x vectors. That satisfies the system or solves the matrix equation. All right, there's a nice visual. Well, first of all, let me give you a more formal definition. First of all, we will shorthand null space of a particular matrix, just NULA. And that is the set of all vectors such that that vector has to be in Rn and it has to solve this matrix equation. That's a tighter, more formal way to see what we set up here. And I always like a nice visual. So picture this. Let's say I've got a set of all Rn, all these, this little flat rectangle contains all the vectors in Rn. And let's say I've got a similar thing over here, Rm. So inside here, I will identify some points. For instance, and let's say there is a whole set of these points that I'll put on a line. And let's even say one of those is the vector 0. And if I were to transform all those vectors, the set of them that all get sent to the 0 vector, that collection of vectors over here that all get sent to the 0 vector, that is my null of that matrix. So the null space is a set of vectors that all get sent to the 0 vector in Rm. So let's go back to that original matrix at the top of the page. And I'm going to check something. Is this vector, does it belong to the null space? Well, let's try it. Here's the original vector, matrix A, and I'm going to multiply it times 4, 2, 0, the way we're used to multiplying. So here we go, row times column. That would be 4 plus negative 4 plus 0, negative 12, positive 12 plus 0. Check. The answer is yes, 420 is in the null space. But that's just one of them. Let's go ahead and get the entire null space. If I were to take that matrix and row reduce it with either my calculator or by hand, let's get there in one step. You would end up with this, my row-reduced echelon form matrix. Now, remember, we've just row-reduced this. This is part of a system of equations, homogeneous. It may help, if you would like, to augment that with the 0, 0 vector. It wouldn't change anything. It may help you remember what we're doing. But what I'm going to call out are my 3 variables that I know right now. We know that any column that doesn't have a pivot is a free variable. So that would be column 2. So we give that its own free variable form. And we then define the others in terms of that. So that would tell me x1 is positive 2 x2s, and x3 is just 0. Well, we've seen this before. Here's my solution if I were to unscale that x2 out. I'd be left with 2, 1, 0. And it turns out that this represents my entire null space. It's the vector 2, 1, 0 that can be scaled by any real number. So, how would I state that? The null space of A is the span of that single vector, which I will put inside my set notation. That's it. So my null space of that matrix is the span of a single vector, and we know geometrically that's a line in R3 going through the origin. So another thing, a null space is a subspace, a very famous subspace, and we always like to call out of what vector space? Of R3, because it contains 3 elements. All right, let's try that one more time. So another way we could be asked the question, let's say we are asked to find the spanning set for the null space of a new matrix. I'm going to give it in reduced form so we don't have to spend time reducing it. So we can have a given matrix. We can see my columns are in R2, but there are 4 variables, which we will call out x1 through x4. Let's identify my free variables. It looks like x2 and x4. Let's define the others in terms of x2 and x4. x1, 2 x2s, x3, 0. So, if we were to put this in parametric vector form, it looks like we've got x2 scaling 2, 1, 0, 0, added to x4, which is scaling 0, 0, 0, 1. And we almost have it. Let's make this go down easy. I'm going to give those 2 vectors names u and v. We're asked to find the spanning set, so here it is. The null space of A is the span in set notation of vector u and v. And we could also then say the null space is a subspace of R4.